A matrix can push, stretch, rotate, and shear space. Most vectors change direction when the transformation acts on them. But sometimes a special vector keeps pointing along the same line. It may get longer, shorter, or flip through the origin, but its line is preserved. That vector is an eigenvector. The factor by which it is scaled is the eigenvalue. Together, they reveal the stable directions hidden inside a transformation. An eigenvector is not special because of where its arrow ends. It is special because of its direction. After the matrix acts, the output vector still lies on the same line through the origin. That is why the zero vector is excluded. It has no direction to preserve. For an eigenvector, the matrix behaves just like scalar multiplication. Instead of mixing the vector into a new direction, the matrix only scales it along its own line. The eigenvalue describes the action along an eigenvector direction. If the eigenvalue is greater than 1, the vector stretches. If it is between 0 and 1, the vector shrinks. If it is negative, the vector flips to the opposite side of the origin. If it is 0, that direction collapses to the origin. So an eigenvalue is a geometric construction attached to a stable line. Different transformations make eigenvectors easier or harder to see. A diagonal scaling usually keeps the coordinate axes as eigendirections. A shear may keep one axis fixed while dragging everything else. A pure rotation in the real plane may have no real eigenvector at all, because no non-zero vector keeps its line. This is an important warning. Eigenvectors are powerful, but not every real matrix gives us a full set of real stable directions. The equation AV equals lambda V can be moved to one side. That gives a minus lambda I applied to V equals 0. For a non-zero V to exist, the matrix A minus lambda I must collapse some direction. Geometrically, it must have a non-trivial null space. For a square matrix, that is the same as saying its determinant is 0. So the characteristic equation searches for the values of lambda that make a direction disappear. If one vector is an eigenvector, every non-zero multiple of it points along the same stable line. Those multiples share the same eigenvalue. Together, they form an eigenspace. In 2 dimensions, an eigenspace is often a line through the origin. In 3 dimensions, it can be a line or a plane. The eigenspace turns one special arrow into a whole geometric set of stable directions. If we find enough independent eigenvectors, they can become a new coordinate system. In that coordinate system, the matrix no longer mixes directions. It only scales each eigendirection by its eigenvalue. That is the geometric heart of diagonalization. We are not just simplifying algebra. We are changing into the coordinate axes that the transformation itself prefers. Eigenvectors also explain repeated transformations. If V is an eigenvector, applying A once multiplies it by lambda. Applying A twice multiplies it by lambda squared. After many steps, the powers of eigenvalues decide which directions grow and which directions fade. This is why eigenvectors are central in dynamical systems. They describe the directions that dominate long-term behavior. Symmetric matrices are especially friendly. Their eigenvectors can be chosen to be orthogonal unit directions. Geometrically, a symmetric matrix turns a circle into an ellipse whose axes are eigendirections. The eigenvalues give the stretch along those axes. This connects eigenvectors to principal axes. It also prepares us for PCA, where we find the main directions of a data cloud. Here is the core picture to keep. An eigenvector is a non-zero vector whose direction is preserved by a matrix. The eigenvalue is the scale factor along that stable direction. An eigenspace collects all vectors that share the same eigenvalue. If enough independent eigenvectors exist, they give the matrix its natural coordinate system. In the next episode, we will turn that idea into diagonalization and use it to understand matrix powers.